apologies for the bit of a mouthful of a title there, but it is what it is. Is this my clicker? As the sort of title sort of indicates, I'm working at looking at airborne microplastics and trying to improve the quantification of them by improving using a technique called pyrolysis GCMS, which I'll go into in a bit. But so I'll just give a brief introduction of why I'm talking about microplastics at an aerosols conference. Microplastics are a contributing part of particulate matter, which most of you are probably aware of, which is the sort of catch-all term for solid particles suspended in the atmosphere. And it can be separated into a lot of different size categories depending on what you're talking about. But the two main ones that get talked about are PM2.5 and PM10. And these are particularly relevant to a lot of air quality monitoring organizations because they are the primary size fractions that sort of can enter the lung and the deeper lung systems, and which means they have sort of a lot more link to sort of increasing morbidities and health conditions, such as cardiovascular, pulmonary conditions. And in recent years, it has been sort of established that microplastics are a contributing factor to particulate matter, but not as well known as in what way they do contribute to this. So I'll give a brief sort of quick chat, I'll go through this quickly, of where microplastics come from. So there's two sort of primary ways you can get microplastics. You can either produce a product to be a microbead or a microplastic, and these are normally cosmetics or like small bleeds that are used in sort of sandblast cleaners, or you can get secondary microplastics, which are when you have a larger macroplastic material, which is then broken down into smaller sort of particles, and this can happen by generally mechanical weathering or photodegradation are the two primary ones that you'll find happening, and this can happen to sort of clothing fibers that just sort of fall off from you wearing them or washing them, building materials that are exposed to the sort of sun for extended periods of time, they break down, and obviously you get a lot of single-use packaging that's just sort of thrown to just sort of do whatever it wants in the environment and spit out microplastics. And it's important to sort of understand the mechanisms by which you get microplastics, because that can give you some indications on where to predict sources of microplastics to the environment. Microplastic work is a relatively recent sort of part of air quality monitoring, and the initial sort of steps into microplastic analysis primarily focused on microscopic and spectroscopic techniques, which basically involve using either visual identification using a microscope and then sending it off to something like an FTIR or a Raman to confirm the composition of the polymer that you're looking at. But this has some disadvantages. It doesn't work very well on particularly small particles. You lose a lot of the mass information, so you can only identify particles. And you get a lot of difficulty with, if you have a complex matrix, it can be very tricky to spot and identify your particles. My work is looking at using pyrolysis GCMS, which is a analytical technique that I will describe a bit more on the next slide, but I'll just give you the brief overview of the pros here. So the advantage here is that it gives you a mass information of your particles, so you can give you a mass concentration in the atmosphere, which is a lot more closely aligned with existing air quality monitoring. So when you look at things like CO2 or NOx emissions, they are generally measured in grams per cubic meter. That's a similar sort of measurement that pyrolysis GCMS can give you. Unfortunately, it is a destructive technique. You do have to destroy your sample, and you don't get any of the sort of size, shape, count information about it, which is why it's not necessarily a replacement technique for the existing ones, but it's an additional bit of information to give you. So this is a brief description of pyrolysis. In general, it's quite simple. You take a polymer, you expose it to very high temperatures, and this breaks the polymer down into smaller compounds that can be volatilized into a GCMS and separated. And you can then stick them through a time of flight mass spectrometer and use the mass spec to identify the marker compounds. And this allows you to identify the polymer because the breakdown of the plastic polymer material that you're looking at is characteristic to the polymer it comes from. So you get very specific markers from certain plastics, and that's how you can identify and then quantify these mixtures. But if you want to quantify something in any sort of aspect, you need standards that are consistent and relevant to your analyte range, which I will explain what that means. So they have to, when you analyze them using your instrument, the values you get out have to be consistent every time, otherwise you don't know whether the data you're getting out of it is accurate at all, and you have to get relevant analyte ranges. So if your sample that you're looking at has, for example, say 5 nanograms in it, if your calibration range goes from 100 nanograms up to 500, it doesn't matter because it's outside of your range. You don't know if your method's accurate down to that level. One of the issues with using this method for microplastics is these standards just don't really exist at this stage. And a lot of people using sort of this technique for microplastics are doing wildly different techniques. There's no standardization. Everyone uses different methodologies. Everyone interprets their data very differently. Everyone uses very different levels of quality control. And it's just sort of a bit of a mess. And that's part of what my project is aiming to look at, is it's trying to test various ways of doing this technique to help provide standardization for the industry. This picture here is an image of basically the only sort of existing commercially available microplastic standard, made by a company called Frontiers, and it's the one I'm using. A few details about it here in this table. So it contains 12 common polymers. They're all there. They come in a sort of a range of masses inside the mix. And then the last couple of lines of this table are just the markers that I've personally selected to analyze them based on literature and my own particular work. And then the successful limit of quantifications that I've managed to achieve by sort of various techniques of milling and diluting the sample down. But my target for this was to try and get reproducible calibration using this mix at low concentrations, so be able to get down to the sort of tens of nanograms range of quantifying. And I wanted to achieve a linearity of R squared 0.98, which is a bit of a tall ask, but slightly successful in some areas, less successful in others. The advantage of using this mix is because it has 12 polymers in one, you do only need to produce one calibration mix to analyze a range of things. And because it's a solid mix and the samples in your, so the polymers in samples that are collected will also be solid, you don't have that difference of composition to deal with. The limitations are when you're looking at really low masses, like 10 nanograms of material, you have to have it suspended in a matrix, which in this particular mix uses calcium carbonate, but that can interfere with the products that you produce when you pyrolyze your sample. Because it's a solid mix suspended in a matrix, it's not necessarily heterogeneous, and because pollen particles are so small, you get agglomeration. It's very difficult to guarantee heterogeneity, especially when you start getting smaller and smaller masses down there. And because you have the such a small mass that you're trying to weigh out, you get inconsistencies just from human error that are kind of unavoidable. So this is an example of some of the calibration curves that I have successfully made. And as you can see, so on here, the green lines are my limit of detection, and the purple lines are the limit of quantifications that have been calculated statistically based on the regression of these curves. And as you can see, for some of them, they're okay, but for other polymers, the quantification limit is very high up my calibration range because the just sort of the linearity is not good enough to get that reliable quantification limits low there. And the reason polyurethane, the one on the left there, is so good is because it's a lot higher mass in the sample than the other two. And this is just really highlights the limitation that if you're trying to look at really low concentrations, it sort of compounds the issues that you're dealing with. So my application for this at the moment, I'm working on at the moment, is I'm collecting samples around London to look at the composition of microplastics in these environments and see if they can be, changes in these environments can be linked to suspected sources. So I have a range of sites here. So I've got a high traffic street to look at tire wear, rubber materials. There's an artificial turf and running track at the Linford Christie Stadium. So I'm looking at the rubber crumb and the materials used to make those pitches. There's a laundromat just down the road from my office, and I wanted to look to see if we can see the polyester nylon fibers coming out the exhaust from there. And then there's a big waste processing facility down by the river, and they handle a lot of the waste recycling in the area. And so they've got a lot. I've been there to do my sampling, and they've just got massive piles of sort of plastic that's crammed together and compacted, and then just sort of left off to one side. And who knows what's coming up of there. And then to sort of compare it all to, there's a wetland site there in Barnes that I use as a background site, which is theoretically relatively low in plastics in the atmosphere. So my samples were collected using this sort of device you can see here, which it's hard to tell from this picture, but it's very simply just 4 pumps in a big suitcase hooked up to some portable drill batteries. And I sampled for 6 hours a day. And the reason I sampled for 6 hours a day is because that is about how long you can maintain the flow rate of 10 litres per minute off those batteries before they need recharging. It's one of the limitations of trying to sample in remote locations. But I'm collecting a range of filter masses. So I'm looking at PM10 and 2.5, and I'm getting samples for pyrolysis and samples that can be used for mass analysis. And these are all cleaned using a multiple furnace at 600 degrees for an hour to remove any plastic contamination from them before they get used. And this is just, unfortunately, I've been having, because of the difficulties with developing this quantification, I do not yet have my calibration standards finalized, so I haven't been able to analyze most of these collected filters. But I have analyzed one of my collected samples from my background site just to get an idea of how well my method was working. And as you can see, a lot of the samples here, a lot of the polymers here are below my limit of detection and my limit of quantification, but some of them are really elevated. And I think those might be due to errors in the method and errors in the mass spec identification that I've employed. But the other big thing to point out here is that the field blank is very consistent with the triplicate analysis that I've done here, which supports my idea that this is a relatively low background site, because the actively sampled air hasn't shown an increase in polymers, but it does highlight a potential error in my collection, transportation, storage, it causing this sort of contribution. And that's pretty much all I've got time for. But a quick conclusion. So I hope I've highlighted the difficulties of quantification. I've made some really good progress, and I want to just add some liquid calibration options to my work to sort of coincide with the solid work. And then I will analyze all these samples, and hopefully next time I see you, I will have results.
Henry, do we have any questions? Yes.
Just a clarification. I don't know if I heard you right. Did you say that your control site was a weapons site?
Wetlands. So it's a wildlife reserve. Yes, they are. As from all of my visits, I haven't spotted any weapons yet, but I will keep an eye out.
Over here, James.
Thanks for the talk. All of these sites you've chosen for the examples of being things which are relatively new produced plastics. I think a lot of the interest in microplastics will be in sort of water supplies, food supplies, more aged plastics. Will these calibration standards be applicable for some more aged samples?
So this is sort of an area of debate in the field of microplastics work, because it is unclear the extent to which weathering processes will influence the breakdown of polymers. It depends a little bit on the specific formation method for the polymers and what the weathering process has done to affect the surface sort of structure of the project. So it's very difficult to go into in a short period of time, but weathering will alter the sort of side chain groups for some of these polymers. But with a lot of the breakdown products, those chains are removed as part of the pyrolysis process. So the markers you'd see would be the same. There are other polymers where you would see a modified version. So it's possible that you would be able to analyze weathered polymers using this technique, but you'd need specifically specified standards for weathered polymers, and because we currently don't really have standards for normal polymers, I think standards for specifically weathered polymers are commercially way off, and I think if someone was to do that work, you'd have to sort of manufacture your own in-house by artificially producing them.
Rachel?
So I'm desperately trying to think back to my polymer chemistry, which is over 20 years ago. So thinking in terms of hard plastics and soft plastics, which you could potentially think would have different breakdown capacities, is a polymer always going to be a hard plastic, or is it going to be a soft plastic, or does it depend what it's cross-linked with? So if you kind of measured one polymer, would you know that that was a hard plastic or a soft plastic?
So no, you wouldn't. So this is a thing with. So to give a good example of this is PET plastic, which is sometimes used to make food containers, but it's also the exact same chemical composition as polyester used to make clothing fibers. So I can identify it, but I cannot differentiate whether it was a solid particle or a fiber before it went through. I just know that it was that specific polymer. So yeah, you lose any non-chemical information basically, which is why I think for in future works it would be good to run this alongside other existing methods to identify your particles and then do this, depending on what your research question is.
Great. Thanks very much, Henry.